Differential equations are incredibly useful, and when we solve them, we end up with these one-parameter families and n-parameter families of solutions, which, when we graph them, gives us a selection of different possible solution curves for our differential equation. One question that you likely have is, how do we know which one? How do we know what solution to go with? So there are a couple of ways that may happen. Differential equations are used with applications all over the place. One of the ways that they end up used is that we know an initial value that whatever is going to take, and then we believe it behaves like this differential equation beyond that. So we can solve the differential equation, and then we can use the initial value to solve for the parameter value, and then we know the particular solution within the family that we want for that particular application. We're going to talk about those types of problems today. Those types of problems are called initial value problems. Now, an initial value problem means that we have some kind of initial condition that's given to us to go with our differential equation that we're solving. So when we have an initial value problem, there are two driving questions that we need to ask. The first is, does a solution of the problem exist? And second, if a solution exists, is it unique? So when we're dealing with first-order initial value problems, there are two questions that we need to answer to be able to answer our existence question. The first is, does the differential equation possess solutions? So when we go through and solve it, is there a solution of any kind? Do we have any of these one-parameter families, n-parameter families of solutions? Are there particular solutions? What do we have? And second, do any of the solution curves pass through the point that is our initial condition? So it might be that we can solve our differential equation, but then none of the solution curves are going to pass through our initial point, which means that the initial value problem doesn't actually have a solution. The differential equation has some solutions, has those solution curves, but none of them pass through that initial point, meaning that initial point paired with that differential equation is not possible, so a solution does not exist. To answer the uniqueness question, we just need to answer one question with our first-order initial value problems. And that is, when can we be certain that there is precisely one solution curve passing through that initial point? So it might be that we have multiple solution curves all passing through that initial point. Hopefully you have kind of a picture of a graph in your mind about what that might look like. So we actually have a theorem to help us out with this. And the theorem is for the existence of a unique solution. So if we let R be a rectangular region in the xy plane, and we have A and B as our bounds on x and C and D as our bounds on y, and our initial condition point is contained somewhere in that rectangular region, not on the boundary, but in the interior. Then, if we have a function in x and y, and the derivative of y with respect to x, so those are the partial derivative signs, but they could be the regular derivative. It just is the derivative of y with respect to x there. If those two functions are continuous on a rectangular region, then there exists some interval, we call it I sub 0 or I sub naught, I naught, where we can take some value h that's greater than 0, and we can subtract it from our initial condition on x and add it to our initial condition on x. And that's going to give us an interval on that x-axis, this initial interval. And that interval will be somewhere in the closed interval AB. And we have some unique function y of x defined on that initial interval. That's the solution of the initial value problem. That all may seem a little bit confusing, but remember, intervals need to go with differential equations when we're talking about solution intervals. And all this I naught is, this initial solution interval, is the subinterval of our solution interval that we have that contains this particular solution with this particular initial value. You may be thinking, that's all well and good, but I still have no clue how to solve these things. That's okay. All I need you to know right now is that if you're given a family of solutions, so some number of parameters, some number of constant values, and the initial conditions that you need to solve it, you can find the particular solution, or you can determine if there even is one or if it's unique. So if there's only one constant, you only need one initial condition. If there's two constants, you'll need two initial conditions. This is just like solving a system of equations. Now, if there's just one initial condition, it will be an XY pair. If there's a second initial condition, what it's going to be is the value of the derivative of y with respect to x at some given x value. So if you're trying to find that one, you'll have to take your family of solutions that you have and take the derivative of it in order to plug in values to solve for one of your constant values. This will really feel like you're solving a system of equations like you did in algebra using the substitution method. You'll solve for one constant value at a time. Now, I know that that's not super satisfying because you're still looking at this differential equation going, I don't know how to solve that. But remember, that's the purpose of the course, is to learn how to solve those. So we've got to pick away at it one piece at a time. And this first piece here is when we're given initial values, how do we find those constant values? How do we even tell if the particular solution that we're searching for even exists, or if it does exist, if it's unique?